guys. So this is the last part of chapter 4 that we'll look at this semester. We'll delve into some of the factoring when we come back from the break. But this is the last thing we'll be looking at. And what this is Descartes' rule of signs. What this will tell us is the possible number of positive, negative, and complex solutions that we can have in the different setups. So, Descartes' rule of sign, let f of x equal this here. And again, this here, this entire deal, is just the general way of describing any higher degree polynomial function. So if we have a higher degree polynomial function, be a polynomial function with real coefficients, the number of positive real zeros for f is equal to, get a highlighter, is equal to the number of changes in signs of the coefficients of f of x, or is less than this by an even amount. The number of negative real zeros of f of x is equal to the number of sign changes in the signs of the coefficients of f of negative x, or is less than this by an even number, or minusing it by 2. Okay, and this will make a little more sense when we look at an example. So to define the number of possible positive zeros, we need to look at the sign changes of the coefficients of f of x. Well, they already gave us f of x. It's this right here, yes? So from here to here, did we have a sign change? Okay, so that's 1. How about from here to here? Okay, so that's 2, here to here. 3, from here to here. No. So how many sign changes did we have? 3. So for our positive numbers, positive solutions, we could have 3 or any number less than that by an even amount. So we could subtract 2 from it. 3 minus 2 is 1. 1 minus 2 is negative 1. So we're done because we can only have real number positive integers for the number of solutions because we can't have a negative amount. Okay. That's all we need to do for the positives. Now for the negatives, it's saying that we need to look at f of negative x. So what we're going to do is we're going to plug a negative x in for every x in the entire equation, which means we'll have is equal to negative x to the 6 minus 2 times x to the negative x to the 5th plus 3 times negative x to the 4th minus 10 times negative x to the 3rd minus 6 times negative x squared minus 8 times negative x minus 8. So we're plugging negative x in for every x in this entire equation. Any questions on this so far? Now we do need to resolve all of the parentheses here. Negative x times itself 6 times. What's going to happen to that sign? It's going to be positive because anytime we put a negative 1 to an even power, it's going to be positive. So this is just going to become x to the 6th. Our next term is negative 2 times negative x to the 5th. So this would be plus 2x to the 5th. So really, anytime we have an even power for this here, this sign is going to stay the same. And anytime we have an odd power, the sign is going to flip. So our next one is 3 times negative x to the 4th. Well, that's still going to be plus 3x to the 4th because 4 is in even. Our next one is negative 10 times negative x to the 3rd. odd power, so the sign is going to go from negative 2. So we'll have 10x plus 10x to the third minus parentheses negative x close parentheses squared. Positive or negative? Negative 6x squared, because the square is going to make that negative x positive, so the signs will remain the same. Well, negative 8 times negative x is going to be plus minus 8. Questions on how we got to this new equation? Let's count the sign changes. So from x to the 6th to x to the 5th, no, positive to positive. X to the 5th to x to the 4th. No, because positive to positive. X to the 4th to x cubed. X cubed to x squared. Well, there's 1. X squared to 8x. Yes, because it's going from negative to positive. And 8x to negative 8. So we have a total of 3. So our negatives could be 3 or 1, because we take whatever the top number is for the sign changes and start subtracting 2, so we can't anymore, we hit a negative. 0 will work, because we can't have 0. Any questions on this here?
So how do you take whatever top number it is?
Yep, because is equal to the number of sign changes of the coefficients of f of x, or is less than this by an even number. So it could be 2, 4, 6, 8, 10, 12. 2 is the smallest one. I just take the top one and keep subtracting 2. All right. Now, we can have positives, as we've seen so far. We could have negatives as positive or negative real numbers, which include our rational and irrational. And we can also have complex, because these are our terms with I. What was the most positive numbers we could have? What's the most negatives we could have? What is the total number of solution? 6, yes? So if I have 3 positives and 3 negatives, do I have all the solutions? So we would have, so 0 complex, huh? So if we had 3 positive and 3 negatives, we have all 6, so we're good, yes? Now, it could also be the case that I do have 3 positives and how many negatives? 1. Because the number of negatives we could have is 3 or 1. And I normally go through all the negative possibilities first. So 3 is the most positive, 3 and 1 with negative. Now with this second case, we have 3 positives and 1 negative, yes? Which gives a total of 4, yes? How many are we missing? So that would mean there would be 2 complex. Well, that's all the different negative cases we can have, 3 and 1, yes? Now positive could be 3 or it could be 1, because we could have 1 positive and how many negative? So how many are we missing? Or it could be that we have 1 positive and, which would mean 4 complex. Because this should always total up to how many? 6, because the degree tells us how many solutions we should have. So any one of these rows should always add up to be 6. Any questions on this here? Now this one here, out of all the ones we'll do today, actually works out to have the nicer solutions. And it actually works out to be 1 plus or minus the square root of 3, plus or minus I, and plus or minus 2I. So any of the ones we're doing today, we won't actually solve for the value of x. They're not meant to be solved for the skills in what we have here. It takes higher stuff than this here, and most likely even with the background I've had, it would be approximations. Any questions on this here before we look at the next one? So when we look at positive and negatives, we're really counting the sign changes, yes? So when we look at this here, we can go on and get the positives just straight from this. Because if we look at the sign changes from all of these here, we can just count them up. So x to the 6th to x to the 5th. Yes, because it went from positive to x to the 5th to x to the 4th. No, so I just put an x. X to the 4th to x to the 3rd. 2. This would be our second, because we're going from negative to positive. X cubed to x squared. No, positive to positive. X squared to x. No, x to negative 9. 3. So the number of positive solutions is 3 or 1. Because again, we take the number of sign changes and then just start subtracting 2 from it to get the rest. Any questions on this here? Now for the negatives, what do we know about the even? Because I'm going to do this little jump, and if y'all feel uncomfortable with it, that's fine. We can go back to the other way. Okay. What do we know about even powers? A negative to an even power stays the same. It's positive, yes? And if the power is odd, it's going to change. So for us here, f of negative x, and this is how I would do it, and I look at it. Okay, well, the first one's 2x to the 6th. It's even, so it stays the same. The next one is odd, so the sign will change. So since it's negative, it's now positive. The next one is even, so the sign will stay the same. So the power is 4 is even. So we're looking at the exponents. Because if the exponent's even, the sign stays the same. If the exponent's odd, the sign will change. It will flip to the third, because our third exponent is odd. Our 10x squared, since the power is even, will stay the same as plus 10x squared. Plus x is going to become minus 9, because the constant term, we won't do anything with it because it does not have a variable attached to it. Because we could put the x in parentheses with the negative and then apply the power, or we can just go on and apply the power. So if we look at this here, x to the 6th, x to the 5th does not change. X to the 5th to x to the 4th, 1. X to the 4th to x to the 3rd, no. X cubed to x squared, x squared to x. So our number of negatives is, well, 3 and 1. So incidentally, it worked out to be the same as the first one. So once we have this, we can set our table up. Positive, negative, complex. I really didn't need all that extra. So I will always start out with the most of positive and negatives that I can have, which is 3 and 3. We need a total of? We have all 6. Yep. Then I will just start decreasing the negatives. So 3 becomes 1 for negative, so 3 and 1 is 4, which leaves us with 2. I can't decrease the negatives anymore because those are our only 2 options. So I'll decrease the positive by 1 and do it again. So 1 and 3 gives us 2. Decrease the negatives again, 1 and 1, 4. And that's it. Questions on this here? We ready for the next one? We'll do 2 more of these and then we'll be done. So let's count the sign changes. So 4 to cube would be 1. Cubed to squared would be. Squared to x is 3. And x to constant term would be. So the possible positives that we could have is 4. Because we could have 4, 2, or 0. So it could work out that we don't have any positive solutions. Now let's look at the negative, f of negative x. So again, if the power is even, the sign will stay the same. If the power is odd, it's going to change. So 3x to the 4th is going to be, stay positive. The negative 7x cubed, the sign will change from negative to positive, so it'll give us 7x cubed. The positive x squared will stay the same. The negative 13x is going to switch plus 8. Because they are all positive. So the number of negatives is 0. Actually, we do have room right here. Positives, negatives, complex. So we could have 4 positives, 0 negatives, and 0. Because how many solutions should we have? 4. If all 4 are positive, we have all 4. Well, I can't decrease the negatives at all because it's already 0. But we can decrease the positives to 2, 0, and then we would have 2 because we need a total of 4. Can't decrease the negatives, so we can go 0, 0, and 4. So these are the 3 cases that we could have. Right. There's 4 total. Now, the reason that this is helpful is because combining this with in behavior in the graph. So if I'm looking at this here and I see that the graph crosses the x-axis once on the positive side, we know we have to have what? Either 2 or 4. It's going to cross again on the positive either 1 more time or 3 more times. It's telling me how many solutions I have. Where on like the previous one here, if I see, because this is just a completely made up graph, that I have something like this here, and we can say it goes back up, curls down and goes up, or something over here. Well, it's crossed the negative how many times? Twice. What do I know I need to have? Well, the only way that I can have 2 negatives show up means I need to have a third, because how many negatives can we have at most? 3, or so if 2 show up, I know I have to have a third one somewhere. Does that make sense? So it's kind of telling us what zeros should occur, what should happen. It gives us a better idea and understanding of what numbers we should be looking for. That's what in behavior does as well. It's both telling us what should we expect? What do we think should happen or should occur? This is the last one we'll look at. Actually, I think it's the last one. Well, yeah. Because I think there's one more after this and then it's out. Yep. Okay. Oh, so they're out of order a little bit? Okay. Now here, we are missing x squared, yes? Doesn't matter. We don't have to add it back in. We're going to go on and count the sign changes for positive. Well, x cubed to x, no. 9x to 25 would be 1. So for our positive, we have 1, or that's it, because we can't subtract 2, because if we do, we'll hit a negative number. Now the negative case, f of negative x. Well, the x cubed would become negative x cubed. Then 9x would become 9x minus, negatives would be 0 because they're all same. They're all negative, so there's not a sign change at all. Well, this one only has one setup, positive, negative, and complex, because I could have one positive, 0 negatives, and because the degree is 3, so we should have 3 solutions. So if one of them's positive, 0 negative, I'm missing 2. Because the degree of the polynomial will tell us how many solutions we should have. Questions on this here? Now, I can tell you the solutions for this one here, because I didn't work it out. I ended up having to look them up and have a system actually calculate this for me. And I don't remember them off the top of my head. Because P can't be less than 0, because our next one would be less than 0. Now it works out that x is positive and is approximately, well, don't erase, 1.9517. Or it could be negative 0.9759 plus or minus 3.4434 I, approximately. Now, really the answer for this doesn't matter, but if we wanted to be a little more precise, the real part, and I'm only going to do the real one, got ahead of myself, 1/2 that there's the actual real answer for this here. And the complex answers are just as complicated. So they made those intentionally not to be solvable. But that is it for chapter 4. There are other components to it that we could look at, but that is all we're going to do for this semester and all that we really have time for, because we only have one more week for the break.